As you can see from the title on the board, this tutorial is about measuring gases and solving gas law problems. This is the second tutorial that you'll see in this chapter, and it will cover more of the math end of things that we are about to go into and attempt to show you how to stepwise go through all these problems. Before we can tackle the gas laws themselves, you have to understand how we measure gas properties. To this point, we have worked predominantly with liquids and solids throughout the course of the year. We use things like the balance to measure mass, and we use things like grad cylinders to measure volumes. Gases are a little bit more tricky due to the properties they possess about expanding. We have to find different ways to trap them and different ways to measure. Three of the most common measurable properties of gases are the ones I'm about to list. The first is volume. The volume of a gas can remain constant if we trap it inside of a container. Units are always important as we go through these. The three most common units that we will use to measure volume are liters, milliliters, and cubic centimeters. We have done conversions with each of these before, but as a little refresher, a milliliter and a cubic centimeter are one and the same. Both of these things are smaller than a liter. A liter has 1,000 milliliters in cubic centimeters. Second measurable property is temperature. Three different ways we measure temperature. However, in here, we always focus on metric, so it narrows us to two temperature scales, that of the Celsius scale and that of Kelvin. The last measurable property of a gas, and the newest, is pressure. I will give you a functional definition of pressure that is a little different from the one that you'll see in your book, but units remain important here as well. The ironic thing about pressure units is the one that you may be familiar with, PSI, which is what your car tires are measured in, for instance, is the one that we will not use in the class because it's not metric. The metric units for measuring pressure are atmospheres, millimeters of mercury, torr, pascals, and kilopascals. Each one of these gets used in different situations. Atmospheres is probably the most commonly used measurement of pressure. It is the most extensive in terms of volume, right, of pressure that will be measured. Millimeters of mercury arises when you talk about the function of a barometer, which I will go into here shortly after we finish with what we're talking about. Torr and pascals are both named after scientists who did very influential work regarding pressure. Torr is named after an Italian chemist named Torricelli, and Pascal is named after Louis Pascal, who also did very important work with gases. The Pascal is technically the standard unit of pressure, but we will not tend to use it all that much because it is a little bit dated. I said that I would give you a functional definition of pressure as we go through. If you look at your book is going to tell you that pressure is force exerted over an area. But that doesn't help us wrap our minds around it all that well. So in an attempt to tie this into what we've done in earlier parts of the chapter, where we looked at gases moving around as molecules all the time, we will define pressure as the number of collisions between molecules and each other, or the container that they are contained in. So if you think back to that program we did from the University of Oklahoma State gas laws, we had molecules moving around in that piston chain. Right? And if we wanted to define pressure of those, we could simply count the number of times they collide with each other or the container, and that will give you a visual representation of what is happening with the pressure of those particular gases. I said that the millimeters of mercury relates to how a barometer works, and I wanted to talk quickly about how that happens so that you can understand. A barometer most often is seen when we talk about weather forecasting and we want to talk about atmospheric pressure in terms of what's going on. Here is how a barometer essentially functions. You take a tube. And when the barometers were originally created, like those tubes had a vacuum inside. Remember, a vacuum is an area where there are no particles. And if there are no particles, there can be no collisions. And with no collisions, there is no pressure. So inside the vacuum, pressure equals 0. Then what they did was they took that vacuum-filled tube and they put it over top of a substance. Right? The tube would be immersed into a pool of an element, and when they originally did it, before they knew of the many dangers of that element, it was mercury. The tube itself has markings on it. And the markings were originally in millimeters. So you can see where the unit millimeters of mercury gets its origins, because they would measure a change in the height of the tube, millimeters of what? Mercury, hence millimeters mercury. Here is how the liquid level of mercury in the tube changes. There is no pressure inside, so there are no molecules to push back on the surface of the liquid. However, outside of the barometer, you have a bunch of molecules that are in the air. For instance, nitrogen, carbon dioxide, oxygen. These molecules all will strike the surface of the liquid, and the more molecules that there are in the air, the more they push on the liquid mercury, it would move up the tube to a higher level. We would get a greater pressure. If the air were particularly thin that day, there would be less molecules to collide with the surface of the liquid. Less molecules colliding meant that there was not as much of a force pushing up. The mercury level would recede down because there was no internal pressure to stop. That's how a barometer functions. Because we'll be using all of these different pressure units, I want you to have some information about how we convert between them. And we will come back to this when we start into our gas laws, but I want you to have it before that so that it's not brand new. In class, I call these pressure conversions. And you have to know relationships so that you are able to do bracket problems converting atmosphere to torr and torr to millimeters of mercury. And here are the most important relationships. 1 atmosphere is equal to all of the following. 760 millimeters of mercury. 760 torr. 101.3 325 kPa, 101,325 PA. Because they're equal, that means you can set any one of these over each other in a bracket problem to convert. Also, because the 760 and 760 are the same, you now know that a millimeter of mercury and a torr are one and the same thing. If we shift over here, we can start to talk about relationships between these. And we did a lab in class where we did a gas simulation using a program called Future Lab. And if you need it, you'll have to come see me because that's one that I can't really post it online for you. Right? But we developed a bunch of relationships between pressure and volume, pressure and temperature, and and volume and temperature. Once upon a time, 3 different scientists did the same thing, and each created a mathematic relationship to each other so that they could figure them out. We'll discuss those 3 gas laws right now. The first of them is called Boyle's law. Boyle's law relates volume and pressure. What they found, and hopefully what you found as we went through, is that these 2 things are related inversely. What that means is that as one goes up, the other goes down, or as one goes down, the other goes up. They always work opposite of each other. Boyle's law problems find their way into our everyday world in a couple places. Anytime you think about changes in pressure, the easiest way to do so is through elevating or dropping. Right? And if you think, where do we elevate most frequently? It has to do with flying. Right? If you think about it, as we go up into the air tends to be what we call thin. Right? If the air is thin, there is less pressure. That means gases have a tendency to expand. So that when we look at airplanes, they have to account for these things. Right? That their gases in the plane are going to try to expand. And they need to make sure they don't expand so much that they damage the integrity of the plane. The other place that you will see it is if you've ever been scuba diving, there is a phenomenon that is called the bends. We will revisit this idea a couple different times, but the idea is that your blood has gases dissolved inside of it. As you dive deep down in the ocean, or in your swimming pool for that matter, you can feel that there's an increase in pressure. Usually you feel it in your ears. If the pressure gets to be so great, like it is when you scuba dive, your blood has the volume of the gas decrease. The pressure goes up, the volume goes down. That's not really a big deal. Where things become a problem is when you rise back to the surface. As you come back up to the surface, the pressure goes down. The volume of those gases in your blood tend to want to expand. And if they expand too quickly, your blood vessels, your arteries, can only withstand a certain amount of volume expansion. They can be ruptured and cause problems. Right? That is what they call the bends. There is more to it than that. There is something called Henry's law behind it as well, which has to do with how much gas is dissolved in your blood, but we'll come back to that later. Right? Boyle's law relates volume and pressure. How does it do so? Through this equation. P1 V1 equals P2 V2. If you remember from the demonstrations we did, this is only true at constant temperature. What do each of these things mean? P1, P obviously stands for pressure. The 1 means the first pressure, so it's the initial pressure. V1, therefore, is the initial volume. P2, final pressure. V2, final volume. The good news about all of these gas laws is I'm going to teach you, right, a method for solving, and it applies for all three of them. Right? That involves kind of a 5-step system. I'm not going to list what they are because you'll get the idea as we solve the problems. But the first thing we'll always do is pull the numbers out of the problem and identify what they are. Second thing we'll do is we'll pick an equation based on the numbers that we see. Third thing we'll do, right, is we'll rearrange that equation to find what we want. Fourth thing we'll do is we always make sure that our units match and that our temperature is in Kelvin. And then the last thing that we'll do is we will plug in and we will solve, watching for our sig figs and our units as we go. There is an overhead in the handout section that has all of your Boyle's, Charles, and Gay-Lussac gas law problems there. If you have yet to print it out, go ahead and do so. I'll read them to you as well, but it's a lot easier if you have it in front of you. First Boyle's law problem says, if the pressure inside of a balloon is 720 with no decimal millimeters of mercury and has a volume of 190 milliliters, what will be the volume of the balloon if the pressure is increased to 0.92 atm? So the idea behind this is going to be as follows. We pull out what each of the numbers are. The first number that we see is 720 millimeters of mercury. The units that go with the numbers are what tell you what it is. Millimeters of mercury measures pressure. So I am going to call 720 millimeters of mercury P1. The second number I see is 190 milliliters. Like, milliliters measures volume. So I will call that V1. Third number I see is 0.92 atm. ATM is a different way of measuring pressure. I'm now all out of numbers. Once I get out of numbers, I list what I'm trying to find. Right? To do that, find your question word. Who, what, when, where, why, how, or maybe calculate or determine. In the question it says, what will be the volume of the balloon? Therefore, I'm looking for V2. Right now, it's very easy to pick an equation because you only know of one, right, given what we've done so far. But later on, you'll have 4 different equations to choose from. You need to choose the one that has P's and V's in it, right? And that is Boyle's law, which says P1, V1 equals P2, V2. Next thing we do is we isolate what we are trying to find. I am trying to find V2. I always say do the opposite of what you see to get V2 alone. I see P2 times V2. So if I want to get rid of it, I will divide by P2. Math class says what I do to the right, I also have to do to the left. On the right side, P2's will cancel, leaving me with V2. On the left side, P1, V1, P2, none of those are the same, none of them cancel. Before I can plug my numbers into my equation and solve, I have to make sure that my units and my temperature are correct. The units can be anything that they want. The only catch is they have to be the same. A lot of times you'll hear me call this apples to apples. For instance, my first pressure is in millimeters of mercury. My second pressure is in atmospheres. They are not the same. I have to make them the same before I can plug in. So I'm going to do a conversion. It doesn't matter which one I convert. I can convert this into atmospheres to make them the same, or this into millimeters of mercury to make them the same. I'll convert the one on the right simply because I have more space to work over there. Right, to convert ATM into millimeters of mercury, it's a one-step bracket problem. I'll put what I want to get rid of on the bottom, ATM, and what I want on top, millimeters of mercury. A little bit ago, I gave you relationships between these, and if you look back, you will find that one ATM has 760.00 millimeters of mercury. Do not let anything in the parentheses here limit your sig figs. It's not like the periodic table where the numbers limit your sig figs. These are exact numbers, so the only thing that limits me is the 0.92. So I'll get out my calculator. I'll do my math. 0.92 times 760 gets me 699.2. Here's the catch. I only get 2 sig figs. So the 6 counts, the 9 counts. Will the 9 affect this 9? You bet. Which will make it 70. 70, however, is not very close to 699, so we add another 0. This is a particularly problematic sig fig thing, because if I don't put a decimal, I only have 1 sig fig. The 7 counts, the 0's down. If I do put a decimal, I get to 3 sig figs because now both zeros count. If I need to have 2 sig figs, I can do one of 2 things. I can put a bar above that 0 to tell me that that 0 is significant, but the second one is not. Or I could write scientific notation, 7.0 times 10 to the 2nd. I like the bar method better. So we will say 700 with a bar mmHg. Now I take a look, do my units match? Millimeters of mercury, yes. Is my temperature in Kelvin? I have no temperatures, so I don't need to worry about it. Now I'm able to plug in. So P1 was 720 mmHg. V1 was 190 milliliters. P2 is 700 mmHg. Now we would do our math and make sure our units and sig figs are correct. So in my calc, I'll type 720 times 190 divided by 700. My calculator says 195.428. Let's take care of units and sig figs. mmHg on top and bottom cancel, leaving me with milliliters. 2 sig figs here, 2 sig figs here, 2 sig figs here means 2 in my answer. So does the 1 count? Yes. The 9? Yes. Here's that pesky case where I have a 5, and the first rule is if you see a 5 is you look to see if there's anything after it. Because there is, that means the 19 rounds up to 20, but 20 is not close to 195, so it's 200. Now it's that same exact problem we had up here. I need 2 sig figs, so I will put 200 with a bar. Second question, very similar. Right, if you look, this time it says a toy submarine has a volume of 37.5 milliliters at a pressure of 770 torr. What will be the pressure of the sub when the volume increases to 0.500 liters? So I'm going to erase this up, and we're going to follow the same pattern again. First thing we do is list what each of the numbers are. First number I see is 37.5 milliliters. Milliliters measures volume. Second number I see is 770 torr. Torr is a unit of pressure, so I will call it P1. Third number I see, 0.500 liters. Liters is a volume, that is V2. Out of numbers, now I list what I'm trying to find. Question says, what will be the pressure? I must be looking for P2. Again, I pick an equation that has P's and V's. That means Boyle's law. P1 V1 equals P2 V2. Then I isolate what I'm looking for, which is P2. I see times V2, so to get rid of it, divide both sides by V2. V2's cancel, leaving me with P2 equals P1 V1 over V2. Before I plug in, I have to make sure that my units and my sig figs are the same and that my temperature is in Kelvin. So I take a look. V1, milliliters, V2, liters, they are not the same. So I'm going to have to get them to be the same. Again, it doesn't matter if I convert this to liters or this to milliliters. Because of space, I will convert this to milliliters. Again, one-step bracket problem. Liters on the bottom, milliliters on top, 1 with liter, 1,000 with milliliters. This just moves the decimal 3 to the right, so it's 500 milliliters, but be careful of sig figs. 3 here means I have to have a decimal. Now I'm ready to plug in. Milliliters and milliliters, my units are the same. Again, no temperature, so I don't have to worry about that. So now I will plug my value. P1, 770 torr. V1, 37.5 milliliters. V2, 500 with a decimal milliliters. You plug this into your calculator. Right? I'm pretty sure that you get a number of 57 point something, but let's take a look. And you get 57.75. Now we take a look at sig figs in units. 2 sig figs, 3 sig figs, 3 sig figs means 2 in my answer. 57.75, all right, the 7 will affect the 7. It will be 58. Units, milliliters cancel, leaving me with torr. 58 torr. Those are Boyle's law type problems. Second gas law we want to look at is called Charles' law. Charles' law relates volume and temperature. These are related directly. Charles' law, the equation's a little different. When we have an inverse relationship, the numbers match. P1, V1, P2, V2. When you have a direct relationship, the numbers are opposite. V1, T2 equals V2, T1. These stand for the same thing, so I'm not going to label them again. Volume 1, initial volume. T2, final temp. Volume 2, final volume. T1, initial temp. The biggest thing you need to remember about gas laws is temperature always has to be in Kelvin. Why does the temperature have to be in Kelvin? The equations only function if there are not negative numbers. Only one of our temperature scales does not possess negative numbers. It is the Kelvin scale. It bottoms out at 0, which is called absolute 0. And absolute 0 is the point where all molecular motion stops. So we have to use the Kelvin scale, otherwise our equations will not work. If you have forgotten how to convert from Celsius to Kelvin, you use this equation. Kelvin is always equal to the degree Celsius plus 273.15. Let's take a look at a Charles law problem. Right? First one on that paper says, what is the final volume of a gas if its temperature changes from 25 degrees Celsius to 0 degrees Celsius and its initial volume was 14.9 milliliters? I claim that we will use the same system to solve for this type of problem, so let's test it. First thing I did before was listed my numbers. First number I see is 25 degrees Celsius. Degrees Celsius is a temperature, so we will call it T1. Second number I see is 0 degrees Celsius. That is also a temperature unit, so I will call that T2. Third number I see is 14.9 milliliters. Milliliters is a volume, so I call that V1. I'm out of numbers, so now I look for what the question wants. It says, what is the final volume? So we are looking for V2. Now I have two equations to choose from. I have P1 V1 equals P2 V2, and V1 T2 equals V2 T1. Given the variables I see, I want to use the equation that has V's and T's in it because it matches the best. So I'm going to write Charles's law. V1 T2 equals V2 T1. Again, solve for what we are looking for. V2, opposite of what I see, is divided by T1, leaving me with V2 equals V1 T2 over T1. Before I can plug in, I need to make sure my units match and my temperature's in Kelvin. Celsius, Celsius, my units match. Temperature in Kelvin, no. So I have to convert these into Kelvin. It's not a bracket problem. We just use this equation. Add 273.15 to this. You do have to watch sig figs. 25 goes 1 short of the decimal, and 273 goes 2 past the decimal. Adding and subtracting, we care about places past. I have to call this 298K and this 273K. Now I'm able to plug in and solve. V1 was 14.9 milliliters. T2, 273K. T1, 298K. Plug this into my calculator. 14.9 times 273 divided by 298. Looks like 13.65 units. K's go away. Milliliters. 13.65. 3 sig figs, 3 sig figs, 3. Does a 1 count? Yes. A 3? Yes. A 6? Yes. Pesky case where there's a 5. First we look, is there anything after it? There's not. If there is nothing after it, you look to the number before. If it is an even, it stays the same. If it's an odd, it rounds up. 6 is an even, therefore it stays the same. Leading us to an answer of 13.6 milliliters. Great thing about gas law problems is they have built-in checks to see if you're right. Here's what I mean. We know that temperature and volume are directly related. One goes up, the other goes up. You can use that to check. T1 was 298, T2 was 273. T went down. According to Charles's law, that means V should also go down because they're directly related. Sure enough, 14.9 to 13.6, that makes me think we did something correct. Okay. Example 2. Go ahead and take a crack at this one yourself. It says, a gas has a volume of 3.06 liters at a temperature of 300 K. What happens to the volume when the temperature of the gas is increased to 745 K, pressure is constant? See if you can use this system to solve, and then check against the correct answer, which I will tell you is 8 liters. Or, if you kept your volume in milliliters for some reason, 800 with no decimal milliliters. Last gas law relates pressure and temperature. This is referred to as Gay-Lussac's law, named after 2 scientists who did work with them, both French, I believe. It relates P and T direct. Because it's direct, that means your numbers are opposite. P1, T2 equals P2, T1. Initial pressure, final temperature, final pressure, initial temperature. Let's take a look at some examples of this. First one says, what is the final pressure of a gas if it has an initial temperature of 31.5 degrees Celsius at a pressure of 0.920 atm, and the temperature is raised to 59 degrees Celsius? Let's use our system. First number I see is 31.5 degrees Celsius. Degrees Celsius is a temperature. Second number I see, 0.920 atm, that is a pressure. Third number I see is 59.0 degrees Celsius, that is a temperature. And the last thing I see, because I'm out of numbers, is that I am trying to find the final pressure. Next thing I'll do here, right, is choose an equation. Now we have 3, right, but the one that has P's and T's is Gay-Lussac's law. So we will say P1 T2 equals P2 T1. Looking for P2, so I divide by T1. I will get P2 equals P1 T2 over T1. Before I plug in, I have to make sure, do my units match? Is my temp in Kelvin? My units, degrees Celsius, we're okay. Are we in Kelvin? We are not. So we're going to have to add 273.15 to each of these guys. If I do that to the top one, I get 304.6 K. And the bottom one, 332.2 K. Notice these both go 1 past the decimal because those went 1 past the decimal. Now I can plug in P1, 0.920 atm. T2, 332.2 K. T1, 304.6 K. Plug these into my calc, 0.920 times 332.2 divided by 304.6. I get 1.0033. I only get 3 sig figs, so 1.00 atm because my Kelvin cancels. Second Gay-Lussac's law problem says a truck carrying a rare gas at 273 has a pressure of 497 torr. The safety carrying pressure for that truck is 825 torr. At what temperature does the gas in the truck become unsafe to carry? If the volume remains constant. Last problem we'll do, let's try to use our system one more time. It says the truck has a 273 K. Kelvin measures temperature. That will be T1. Second number is 497 torr. Torr measures pressure. I will call that P1. Last number I see is 825 torr. I will call that P2. Question where it says what will be the safety carrying temperature? Well, you're looking for T2. This equation fits our variables the best, so we will use P1 T2 equals P2 T1. I'm looking for T2 this time, so I'll isolate that. Divide by P1, divide by P1. I get T2 is equal to P2 T1 over P1. Before I plug in, I have to make sure my units match and my temps in Kelvin. Torr and torr, my units match. Kelvin, we are okay. This one you can plug directly in. P2, 825 torr, T1, 273 K, P1, 497 torr. Torr will cancel. My temperature will be in Kelvin. 825 times 273 divided by 497. Looks like 453.16. I only get 3 sig figs, so we will say 453K. All 3 gas laws we will use. Hopefully this helps you out with any troubles that you're having, but if it doesn't, please feel free to stop in.